So when this says sample 1 and sample 2 are due, what I mean by sample 1 and sample 2 is the packets that you have so far, they say very clearly on the front page, sample exam 2. The new packets you get, the two, the one you get today and then the other one next week, they look just a little different. Here's what they look like on the front page. It just says exam 2. This is from an older book of practice exams. Okay, so that's what I call them. All right, so I call the first ones I gave you, I call those sample 1 and sample 2, and then the other ones I'm going to give you are exam 2 and exam 3. Right, those are the 4 packets you're going to have. So on Friday we'll take our first midterm and we'll hand in those 2 packets, and then that next Monday we'll do our second midterm and hand in those 2 packets. Okay? So, that is what's going on. Now, keep in mind, I know I'm giving you 2 more packets, and what this person who was complaining, in class was thinking they would feel pressured to do those packets this weekend. Well, you don't really have to, because think about it. Once this quiz is over on Wednesday, there's no other homework we will have through that next Monday except those packets. You know what I mean? So it's not like you've got to have those packets done by early next week, right? So after Wednesday, so it's really more about the take-home and, staying caught up with sample 1 and sample 2, even though I'm giving you this packet. And then we'll get ready for this quiz, right? And then it's Thursday, after Wednesday. It's Wednesday night, all Thursday. And really, sample 1 and sample 2 should be getting pretty close to being done, right? So then you got Friday after the midterm and the whole weekend to be working on those. So it's you know what I mean? It's not a big deal. So here's what I told him. I said, okay, here's the 3rd packet. It's here. If you want to take it today, go ahead. But you don't have to. I don't care. Right? You don't have to take it today, because this weekend should really be more about the take-home that's going to be due on Tuesday, probably as your main assignment. Okay? All right. So let's take a look at homework from the book. Let's talk about those first with the 2 theories. Okay? Any questions on any of those? And please ask if you've got them, because they're kind of different kinds of questions. 279, 280. We had ones about this, and then we had, I don't know how far you got during class yesterday, but what, yes, Andy.
So like on the first one, like continuous, does that mean it's just like a value for every y, for every x there is?
That's one of the things. We actually had 3 things that meant it had to be continuous. The formal definition is there must be a value. F of A must be defined, right? Now here I'm recording this and I'm writing this where they can't see, but 2, the limit must exist, which means you can't have any, the cars have to meet, right? And then the 3rd thing was the limit had to equal the output. So let's look at these 2 pictures here. But basically what continuous means is connected, right? The graph has to be connected everywhere. Can't be gaps or holes or jumps. Clearly, these are not continuous, right? I mean, these are the extreme example, right? Right here, this one fails the 3rd one. The limit exists. The cars meet right here. The output is up here, so number 1's okay. Number 2's okay. The cars meet, but they're not in the same place. So this is not connected, right? Because there's this jump up there. Here, the limit doesn't exist. They're not connected. The cars don't meet. And let's pretend this dot wasn't here. Then this would be discontinuous because there's no output there. There's just a hole, right? But basically, continuous means you don't lift your pencil. It's connected everywhere. Okay? All right. So, did we do question 1?
Yeah.
So, where is F continuous? Well, F is continuous from -4 to -3 if you don't include -3, right? And it's continuous from -3 to -1 if you don't include those, right? So there are pieces of it that are connected. But the graph itself is not continuous, right? Meaning the whole thing is not continuous. But there are pieces that are continuous. That piece is continuous. That piece is continuous, right? So that's what that's getting at there. Okay? What else? Well, yeah, go ahead.
Okay, on 22 through 25,
Yes.
were there any of those that it didn't apply to? I was kind of having a hard time figuring it out.
Good. Let's talk about that because that came up in the other class too, and I think that's an important thing. When it talks about, well, sure, but when it talks about on that side of the page, when it talks about does the theorem apply, let's talk about what that means. Does the theorem apply is like saying, does the promise hold? Is the promise in effect? Remember, if you get an A, then you get a car. Under what conditions is the promise in effect? Well, no, I mean about I'm talking about the car. Under what conditions is that promise in effect? If you get an A, right? That promise applies if you get an A. If you don't get an A, the promise is not in effect, right? You might get a car, you might not get a car, but the promise is not in effect because the promise was if you get an A, then you get a car. So that's what this question is saying. So this question is really saying, does the intermediate value theorem apply? Well, what has to happen? And then, Andy, that's what you were saying. For the intermediate value theorem to apply, the function has to be continuous on a closed interval. If the function is continuous on a closed interval, then the theorem has to apply, right? Because it's a promise. It's going to apply. It's a known theorem in math, right? So, 22 says, there were 37 people in this class, now there are 12. It's kind of like this. Yesterday there were 23 people, now there are like 11. Okay, but you know what I mean? There are 37 people, now there are 12. For that to apply, for that theorem to apply, that has to be continuous. Is that one continuous? In other words, the intermediate value theorem says it's got to hit all the y values in between, right? Well, if you go from 37 people down to 12, do you hit all the number of people in between 37 and 12? Number one, you wouldn't have partial people, right? And even then, it wouldn't even go 36, 35, 34 either, right? You might go from 37 down to 30, down to 25, right? So that is not continuous, so therefore, the theorem does not apply. Make sense?
Yeah.
If you don't get an A, the promise doesn't apply about getting the car. It just does. You might get a car, you might not. Okay, keep going. I was 37 miles from home, now I'm 12 miles from home. Would you hit all those points in between? At some point, you had to be all those dis in between. So it's a continuous situation, a closed interval, 37 to 12. So therefore, the theorem applies. Make sense? Okay. I was driving 37 miles per hour, now I'm 12 miles per hour. The theorem applies. You would have to hit all those speeds. As you slowed down from 37 to 12, you'd have to hit all those speeds in between. It's continuous. The theorem applies. I had $37 in my pocket, now I have 12. No, you would not go through all those different things. Okay? Now, and I'm glad you asked that because now let's go back and talk about 7 through 11 or whatever that section was. 7 through 10. Because that's a different question. That question now is, does the conclusion hold? Now that's a different question. So let's think about the car problem. If I ask you, okay, you know, hey Matthew, that was your parents that made you that promise. And I ask you, does the conclusion hold? Did the conclusion of their promise hold? What would I be asking you? Did they give you a car? Right? It's not asking about the first part, right? About the A. The conclusion of that promise was you'll get a car. So if I ask you, did the conclusion hold? I'm asking, did you get a car? Right? Doesn't matter if you got the A or not. I'm just asking, did you get the car? Right? That's what this question is. Because clearly these functions are not continuous. They all ask about -4 to 4, right? So clearly these two are not continuous. So does the conclusion have to be true? Does the conclusion have to hold? No. You didn't get the A, There's no guarantee on the car. Maybe you did, maybe you didn't. So these are not continuous. So maybe the intermediate value theorem holds, and maybe the extreme value theorem holds, but maybe not. So they're just asking, did it? Did it? Did you have nice parents and they gave you the car? I mean, your parents can be nice and still not give you the car, but still, whatever, right? So let's ask the question. So 7, does the conclusion of the intermediate value theorem hold? What's the conclusion of the intermediate value theorem? That it hits all the points between the starting point and end point. So we got to be careful of it. Starting point and end point. So the conclusion is, does it hit all the y values between the starting point and the end point? Certainly not guaranteed to, because this is not continuous. But let's see, where's the starting point? At y value is what we care about here, right? -2. And what's the ending point? This one. See, a lot of people look at this one and think you're going to go from -2 up to 2. No, remember, we said that. It's not about mins and maxes here, right? It's about starting point and ending point. So if we start down here at -2 and we end up here at 1, does the IVT is saying, does this function hit all the y values between those? Yeah. I think it does. Right here there's a hole, but you know what? It's filled right there, right? So it does hit -1. Goes on up here. Goes on up here, there's a hole there, but it hits, I think so. I think there's a y value all the way up from -2 to 1. So the intermediate value theorem conclusion holds. That wouldn't have had to, it just happened to in this one, right? It happened. Okay? Now, if there hadn't been this dot here, then would it have? No, then there would have been no y value of -1 if this dot had not been there. So then it wouldn't have hit. Right? But either way, it's not a problem for the intermediate value theorem. The theorem's not a lie, right? The theorem only holds if this is a continuous function. Okay, what about this one? Starting point is here, ending point is here. Does this hit all the y values between 0 and 2?
Yep.
Right. See, we don't care about that down there. We're not talking about that, right? We're just talking about starting point and ending point. It hits all the y values between 0 and 2. Now, technically, the way the intermediate value theorem is worded, it says, for any y value between f of a and f of b, there is some k such that there's a point in here that has that y value. So pick any point in here, there's somewhere that will have that y value. Well, all through here, they all have those y values. Okay, I just, remember, when you state the theorem, you're going to want a little more exact wording. But when we talk about the theorem, I think it's okay to talk about it has to hit all the y values. I think it's okay to say that. Number 9. Does the extreme value theorem hold? What's the conclusion of the extreme value theorem? There's both a max and a min. That's the conclusion. That's the, you get the car part, right? Clearly, it is not guaranteed to have a max and a min because these are not continuous, right? You didn't get the A. So it doesn't have to have a max and a min, but we're just saying does it. Maybe it does. So on this one, does this one have both a max and a min?
Yes.
-2 is the min, 2 is the max. It does. What about this one?
No.
2 is a max, but there is no min, right? You can't say -2 because it's a holden. You can't say -1.9 because -1.99 is smaller. -1.999 is smaller than that. There is no minimum, but not a problem because it's not continuous, so we're not guaranteed. That's what we're talking about. So, back to Aaron's question, does the theorem apply means, is the first part true, right? Did you get the A? That's when the theorem would apply. If the first part's true, then the theorem has to apply, has to work, okay? But does the conclusion hold is the second part, right? That kind of, all right. Anyway, probably talked about that too much, but that's kind of, if you understand that, then I think you have a pretty good understanding of the different questions you could ask about these things. Okay? All right, let's look at the packets then. Let's look at the packet. Let's sample 2. Let's just talk, give you just a little bit of a chance here to ask about that. And then I want to give you, some work time too. Oh. So in the other class, we spent a little time on some of the free response. If there was one of those you wanted to look at, if you've gotten that far into it, which if you have, you're really in good shape. Like I said, there's 2 more packets, but after Wednesday, you know, Wednesday night, Thursday night, Friday, Saturday, that could all be about those other packets, right? Even though if I give you this other one, you get a head start on it, but I really think your first priority probably is the take home, right?
Could you do number 3 on the free response?
3 on the free response. That's the one that had the B in it.
Yeah.
It's kind of our nemesis again, like I said. I'm hopeful that as much, I talk about it enough, we'll continue to get better at this. It's kind of an interesting problem. It's a really interesting problem. Now, when you take these free response questions, when you put all the parts together, which sometimes you don't care about, all you want to do is get through the parts and do them. But, you know, when you put them together, they kind of tell a story in the problem sometimes, right? This one, it does as well. But again, when we see that B, we just say, hey, let's just pretend that was a number there. Do everything the way we normally would. Don't worry about that B. Well, the first thing they want you to do is just plug in a 1, plug in a 2, plug in a 3 in your calculator, right? And I think when you do that, it gives you a picture of something like this for one of them, and then it goes up something like this for the next one, and then it goes up something like this for the third. Am I right? I mean, it does something like that. So you put a 1 in, so it'd be minus 3x and minus 6x and minus 9x, and right, you just graph those. And you get 3 different graphs. So that's all you have to do in part A, right? Now, in part B and C, it says the relative max and the relative min. What's that mean? That's local max and min. How do we find local max and min? Derivative is 0, right? So let me go where I got a little more room here. So where is the derivative 0? So f of x was x cubed minus 3bx. So the derivative, and then don't we do number lines generally on these? Right? Isn't that what we typically do with local max min? Right? So do the derivative, set equals 0, do a number line. So we get 3x squared minus, what's the derivative of 3bx? 3b, right? Because 3b is just like a number in front of an x. Do the derivative, it's just 3b. And we set that equal to 0. So we solve for x, right? That's what we usually do, solve for x. So we do that, we divide by 3. We do the square root, don't forget your plus minus. And we get that. Now, that's a little disconcerting, I guess. It's not a number, but that's okay. It's a B. Everything in here says in terms of B, so that just means B is going to be in your answer. Let's just pretend those are numbers. What would we normally do? If that would have said plus or minus 3 right there, what would we have done? What would we do? Put them on a number line, right? We would put them on a number line. So we would have a number line. We'd have negative square root of B here. We'd have positive square root of B here. Believe me, this is not the first time you're going to see this, right? You may see it in the midterm, you may see it in the final. One of those times for sure. You know, if you take the AP exam, probably going to see it. It's pretty typical. So you're going to have something weird on the number line, like letters instead of numbers. Well, what do we usually do when we have our number line at this point? Pick numbers in between. Well, the easiest, what's in between here? 0 would be easy. Now, I think it said somewhere that B is positive, right? Didn't it say B has to be positive? Right? Yeah. So we know B's positive. Of course, it wouldn't be in a square root if it wasn't. So we know B's positive. So then the question becomes, what's bigger than square root of B? That is almost always what people say. But, I'll bet if you think about it, Matthew. Yeah, if it's less than 1, it goes the other way, right? You would think you square something, it gets bigger, right? But if you take 1/2 and square it, what do you get? 1/4. So, which actually is littler. So if this would have been 1/4 in here, right? And you squared that, you'd get 1/4, right? Problem is this is 1/2 and this is 1/4, and 1/4 is not bigger, right? So what's actually a way, so squaring a number doesn't always make it bigger. What will always make a positive number bigger? If you multiply by something bigger than 1, right? So how about 2? How about doubling? Doubling a positive number always makes it bigger. So how about 2 square root of b? That will be kind of your fail-safe on a number line kind of thing. And you got letters, and you want to, if it's positive, you want to make it bigger, just multiply it by 2. And then, of course, the same thing would happen over here then, right? Negative 2 square root of b would be littler, right? That way. That will be the thing to do. Now, b would have been nice because we wouldn't have had to mess with square roots. But where are we going to plug these at? Where are we going to plug them? Which is right there. And notice what we're going to do. We're going to square it. So the square root won't be that big a deal, right? So again, just do it. Now I know when you're looking at it, you're thinking, oh God, how am I going to do that? I go, again, don't get caught up in it. Just think to yourself, what do I normally do? If this was a number, I would take it and I would plug it into f prime. So let's do it. So we're going to take 2 square, well, let's do 0 first. That's easy. Put 0 in. We get 0 minus 3b. Well, that's negative because we said b is positive, so that's negative. So we know that's going to be negative. Okay? Now, to be honest, a person can almost skip the rest of this because they asked me for the maximums. They asked me for the minimums. Pretty good bet you're going to have one of each, at least. I mean, you look at my number line. Don't you suppose this would be positive, positive? So you get a max and then you get a min. I mean, I don't know that I would suggest that you just skip this part of it, but I think that's going to happen. But let's just do it anyway. So 2 square root of b, let's plug it in. So we'd have 3, then we'd have 2 square root of b squared, and then minus 3b. So I'm just plugging that in for x. Now, the 3 hang out here. What is this when I square it? 4b. Which is 12b minus 3b, which is 9b, and b is positive. So sure enough, that's a positive. And you know what? We can skip the other one because what's going to happen when we put this in? When we square it, it's going to be the same thing. The negative's not going to matter. So it's going to be the same thing. So it is going to be a positive. So we just figured out our max and our min all at once. So our max, now notice what they want. They want the x and the y coordinate. So the x coordinate of the max is this one over here. So that's negative root b. How do we get the y coordinate? Plug it into the black equation up here. So that's going to be, this is going to be weird. I better put 1/2 power. It's going to be easier. So this is going to be negative square root of b to the third minus 3b times negative b to the 1/2. See what I mean? How that it'd be easier if I had used powers here instead of roots. And this is a no calculator one, I'm guessing, right? No, this is a calculator. Oh, you know, our calculators are good at this stuff, yeah. See, this is where I always think somebody with a CAS calculator would have an advantage. Because, like solving this and plugging b's in, we can actually do that in our calculators, can't we? We can plug in square root of b into here and type it in. Now, you know, I also think, though, that they've started to kind of change how they ask these questions and put these more on the no calculator. Because quite honestly, I think in the past they put this on the calculator part because they want you to be able to draw that graph and stuff at the beginning, you know what I mean, in part A. But now they've got more no calculator questions. I think part of that is for this. But anyway, if you've got your calculator, you could do it, right? But let's just do it as if it wasn't a calculator. So power on a power, that would be b to the 3/2. Here we would add the powers, which would also be 3/2 power, but it'd be a positive 3. So what we have is we can add those up. So negative 1 plus 3, that'd be 2. Let's put it here, 2b to the 3/2. So it actually simplifies pretty nicely. Your calculator might give it to you in a little different version, probably give it to you as roots, maybe. And then the other thing is, I'm not even sure you really, on the AP test, on a free response question, I'm not sure you really even have to simplify that, quite honestly. When you plug that in, if you wanted to leave it like that because you weren't sure how to simplify it as a final answer, that's usually okay. Okay? But anyway, that is what you get. Now, it turns out, remember, think about what we're doing here. It's easy to get lost in the weeds. When we graphed this equation, it went like this, right? They all looked like this. Well, what did we just find? We just found that max, didn't we? Negative, and then a positive y. So the minimum is just going to be this one over here, right? And I think the minimum ends up being, I'll just write it down here, positive square root of b. We know that from our chart here. And then it ends up being negative 2b 3 halves. It ends up being the same thing. And that's this point down here. Positive and then negative. So there's your max and there's your min. And you wouldn't have to redo all the work down here for part C. You got that work up there. Now, part D is really much easier than it looks. I mean, it sounds kind of messy, but it really is not bad at all. Think about it. Show that the max and min points. Now remember, here's what they were. Here was the max point. And here was the min point. Show that those points lie on this function by finding A. What do? You substitute. I mean, but think about that. That's what a function equation is. It's telling you it's all the x and y points on that curve have to work in this. So these are two x and y points that fit on this curve. So just take this and plug it in for x and y. So let's take the top one there and let's just do that. So in place of y, let's put 2b to the 3 halves equals negative a, and in place of the x, let's put negative b to the 1 half. Right? All I'm doing there is taking their equation. I have an x and a y that I found in the earlier parts. So I just take those x's and y's, plug them in for x and y, and look what happens. I get 2b to the 3 halves equals, now this would be negative, power on a power, you multiply, so that's 3 halves. It'd still be negative when you cube it, times that negative, it end up being positive a, b to the 3 halves. Oh, look at that. So what's a?
2.
A's got to be 2. I mean, it looked like it was going to be really ugly and messy, but a lot of times what happens, you just do it, and something nice happens. And A comes out to be 2. And guess what? The same thing will happen if we plug in this bottom. Because if we plug in the bottom one, here would be a positive. So this side would have a negative on it. But over here, we'd have a negative also. So when you divide the negative out, you'd still end up with A equals 2 both ways. So what they're saying is, the max and min points actually... So this is the part you wouldn't have to do, but this is the part I think is interesting to tie this all together. What this is saying is that these max and min points of all those different curves that you drew in the first one, in part A, all of those lie on this cubic. Now that's a negative cubic. A negative cubic does that. Just a negative basic cubic goes like that, right? Well, sure enough, if you go back up here, if you go back to your picture that you drew back here, and you think about it, it goes up like so, and then the other one goes up, okay, that's bad. Goes up like so, and then this one goes up like so. What they're saying is these max and mins, now mine's such a bad picture, but here would be this graph of negative 2x cubed would come down here and then go like this. And all of those max and min points of all that whole family of functions, if you just kept drawing them with different b values, they would all have a max and min that would lie on that curve. It's kind of interesting scenario. Okay? So that's kind of what that problem's about. All right, anything else? We can do another one. You want? 4.
Yeah.
Next. Yeah, we talked about this in the class, so what the heck. It would be good. It'd be good to put the video. Here's why this is a good one to work on right now. Because number one, we haven't done some differential equations for a while, so that's probably going to be on there. Good chance there's one of those on there, some with the slope field kind of thing. We've done some of that. And there's also some other good review here when it talks about horizontal and vertical asymptotes. Okay? So there's some things in here that are good. Now, It brings back some things we've done with differential equations. And this one would be kind of a hard one, I think. But after we do one, maybe in another packet we'll have another one similar, right? It's going to be coming back to us. And then all of these things will hopefully come back to us even better at the end of the year as we review these some more. All right, anyway, we've got this differential equation, which is y prime. Remember, of course, this side here is y prime. Equals that. Verify that this is a solution. How did we do that? We did that. Remember at verify? Remember the T-chart business? That's exactly what we did. Okay? So actually, let me do that on a clean thing here. So what we did is we said, okay, here's y prime, and here's y minus y squared over x, right? And we're proposing that this, no. Am I doing this right? What was their proposed solution?
That was x over x plus c.
They're proposing that this is a solution of that, the original function, right? So on this side, we're going to put what? What do we put over here? The derivative of that. So let's do the derivative of this. How would we do the derivative of this? Quotient rule. So that would be the derivative of the top, which is 1, times the bottom left alone, minus the top left alone, times the derivative of the bottom, which is just 1. All over the bottom square. Right? Well, that's not bad. Now what do we got here? We got x plus c minus x. So that's just c over x plus c squared. Right? Okay, so we're done there. Nothing else we can do there. Okay, on this side, we do what? Substitute. So in place of the y, we're going to put x over x plus c minus that squared, which would just be x squared over x plus c squared. Right? Let me erase a little bit here. Okay, there we go. Right? So I just squared that all over x. Okay, good. This is one of those bow tie situations. But actually, it'd probably be better, instead of bow tying, it'd probably be better just to get a common denominator. This might be the place where a lot of you, I know we struggled with this when we did common denominators. You got to be careful here. How could I get a common denominator? How could I make this bottom have x plus c squared? Be really careful with what you say. How could I make this have a bottom of x plus c squared? Multiply the top and bottom by x plus c. Do not say square, right? You can't square the top and the bottom of a fraction. I mean, think about it. If you have 2/3 and you square the top and bottom, is it still the same thing? It's 4/9. 2/3 and 4/9 are not the same thing. So I can't square top and bottom. What I can do is multiply by an x plus c. I can multiply the top and bottom by x plus c. Okay, that's what I want to do. So now what would I have on top? Distribute that. X squared xc minus x squared. So you can see some nice things are going to happen. All over my common denominator of x plus c squared. And then don't forget that's all over x. Right? Now look what happens. The x squareds cancel. So now I have xc over x plus c squared. And now what can I do with this divide by x on the bottom? So I can multiply by the reciprocal, right? I can bring it up as a 1 over x. And sure enough, those x's then cancel here and here. And so look what's left. C over x plus c squared, which means I got a match. So there you go. A lot of algebra there, right? Is really all it was. We had to do a quotient rule, obviously. So there we go. Okay? Now, so that's part A, right? Now, it says, show that all solutions contain 0, 0. Now, that's a new one, right? Show that all solutions contain 0, 0. Well, what you do then is you just take, this is your solution. We've just shown that that is, right, 0, 0. Well, that's the solution. So what that means is just plug a 0 in for x, a 0 in for y. So you plug a 0 in for y, you get that. Plug a 0 in for x, you get 0 over c, right? 0 over c equals whatever c is. Now remember, it said at the top there, c can't equal 0, right? Didn't it say that? It didn't?
Because c cannot equal negative c.
X.
Or x.
Oh, x can't be 0, and x cannot equal negative c. And x, since x can't be 0, remember, then c can't be 0 either, right? Okay, so that is, so we know that's going to be okay, all right? So 0 equals 0, so that works. So if you put 0, 0 into this, if this is all the different solutions, then 0, 0 does work. So that means 0, 0 is going to be in all of these solutions, okay? Now, that's going to come into play here in a minute. So now it says, write an equation of the particular solution that contains the point 1, 2. Okay, forget this part down here for a minute. Let's just do this. What would the particular, now remember, this is the general solution because we don't know what C is. But now if they give us an initial condition, remember we call this initial value problem? Initial condition, we can figure out what C is. So what do we do with that 1 and that 2? We plug them in and figure out what C is. Okay, so let's do that next. So we're going to take y equals x over x plus c, and we're going to put a 2 there, and we're going to put a 1 in for x. So we distribute that over the 1 plus c, that'd be 2 plus 2c. 2c would equal negative 1, c equals negative 1/2, I believe. I went kind of fast there, but right, just put a 2 in for y, put a 1 in for x, and I found out that c has to be negative 1/2, right? So, our solution now, so the equation of our particular solution is y equals x over x minus 1/2, correct? That is our solution. Now, forget this part, this 0, 0 part. Okay, let's forget that part for a second. All right? Forget, because they keep talking about 0, 0. Why do they keep talking about 0, 0? What's going on? Okay, so let's just forget about that for a second, and let's move on to this next part. Write the equation of the vertical and horizontal asymptotes of this solution. So here's our equation. What would be, let's do vertical asymptote first because it's easiest. On this equation right here, what's the vertical asymptote? X equals 1/2, right? Because what makes a vertical asymptote? When the bottom is 0, right? If you put a 1/2 in for x here, you'll get 1/2 over 0, which is what causes a vertical asymptote. So the vertical asymptote is x equals 1/2. Horizontal asymptote. What's a horizontal asymptote? It's y equals, but where do we look for it? Good. I was afraid I was going to have to go out of the room here in a minute. Horizontal asymptote's way, way out as x approaches infinity. So a horizontal asymptote problem is always asking you what is happening as x goes to infinity. Well, what happens to this as x gets bigger and bigger? Remember the high powers dominate thing? The 1/2 isn't going to matter. It's x over x, which is 1. Or L'Hopital's rule, remember that? Infinity over infinity. So we can do the derivative of the top, derivative of the bottom. So 1 over 1. So the horizontal asymptote is y equals 1. Right? Okay? So we just found horizontal and vertical asymptote. Now all of this we're going to put together now. The slope field is provided. Sketch both branches, both branches, that's weird. Well, whatever. We'll deal with that in a second. That pass through the point 1, 2. Okay, so here we go. So we're going to now graph on this slope field with an initial condition of 1, 2. Well, here's 1, 2 right here. Now, didn't we just say there was a vertical asymptote? Where? X equals 1/2. So wouldn't that go right through here? Right? X equals 1/2 would go right through there. And we said there was a horizontal asymptote at 1, which would go right through there. Correct? Now, let's go with the flow through this point. So wouldn't this have to just go up, 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 up like that? And then come down and go through like that. Correct? Now, but wait a minute. They said both branches. Would you have thought to draw anything else other than that? I wouldn't have, right? I just would have drawn that. I would have said, what about this? Well, I would have thought, well, maybe if you had a different initial condition, you have that. Well, it turns out there's more than one branch. And now, all of a sudden, those questions they're asking about 0, 0 are making sense. In Part B, they said, was it Part B, or Part A, they said, show that all solutions contain 0, 0. Isn't that what they said? And we plugged it in and we said, sure enough, right? We have y equals x over x minus 1/2. That's what we're trying to graph, right? And 0, 0 works in that one. So the graph has to go through 0, 0. This graph doesn't, so there's got to be another branch. Okay, so now let's go to Part B, the one we skipped. The part we skipped. What did it say there? They wanted us to find the slope at 0, 0, because if I now know, let me put a point at 0, 0. So if I now know that this graph is supposed to go through 0, 0, I could draw the other branch. But how would I know where to draw it? Does it go up? Where does it go? Right? Well, what they're telling us in Part B is supposed to help us with this. They said find the slope at 0, 0. Well, if you go up to the differential equation, that is no help. Here's the differential equation. What happens if you put 0 over 0 there? Or put 0, 0 in? You get 0 over 0, which is undefined. So that's no help. But you know what? We have a different y prime. Remember in Part A, the left side of our t-chart? Wasn't that y prime? What did we have there? C over x plus c squared. But what's c now? Negative 1/2. So we could do, we can actually find that. So this is what we should have done back in Part B, but we skipped it, right? So back in Part B, it said find y prime, because remember, this is no help. You said, well, shouldn't it work in both? Well, it said that this y prime is only if x is not 0, right? The original differential equation said x can't be 0. So this won't work, but this one will. So look what we get. Now let's put a 0 in for x here, right? Let's put a 0 in for x. So we'd have negative 1/2 squared would be 1/4. So we'd have negative 1/2 over 1/4. Invert and multiply, we'd have 4 times negative 1/2. What's that? Negative 2. So what we just found is our slope has to be negative 2 right there at 0, 0. That's what Part B was helping us do. So Part A was saying show that 0, 0 has to be in all your solutions. So all the branches have to go through 0, 0. Or all the solutions have to have a branch that goes through 0, 0. And then Part B, we found the slope is negative 2. That's going to help us. And in Part D, they said draw all the branches, both branches. So this is just going to go down like this, and then it's going to come up and level off like that. Whew. That was a tough one, right? A lot of stuff going on. Okay, a lot of stuff going on. But a lot of good review stuff as far as the asymptotes and the limit as x goes to infinity and the t-chart, verifying a differential equation, right? Stuff we've done. Sketching on a slope field with an initial condition, but that was an added twist that we don't run into very often. Okay, so all right. To me, that parts of that one, you talk about free response, right? Free response, you get partial credit. There were certainly some things you could do there. You could have got some partial credit, I think, in that T-chart part of it, right? And some of those various things that you did, plugging in the 1 and the 2, figuring out what C is, right? That kind of stuff. But that's certainly one where that 65% as an A comes into play, right? There's some points there you're probably not going to get, right? Probably you just may not. Okay. All right, but hopefully we have a better chance of getting them than we did 15 minutes ago. All right. So the rest of the time, I got answer books up here. Now this new packet, or well, it's actually older, but these packets here, the free response aren't divided up into no calculator. They're kind of all calculator. And I just circled, you should be able to do all the parts of the free response. If I didn't circle like A, B, C or whatever, it just means do all the parts. But there's a couple free response I didn't even put in here because we couldn't do them yet. So I just in this packet, I just included what you could do. But in the multiple choice, it's still the same thing. Just do the circle ones. Just do the circle ones. Okay, but anyway, take home, you can work on the take home now if you want. You have 30 minutes left. You can work on the take home now if you want. You could work in packets, whatever. Here's some answers for the first 2 packets we got. This is what the answer book looks like for these other packets. It's this white thing. Okay? All right. Yep. You can go.